Usually when you look at a map of a city, there's there's this expectation of simplicity, right? Like reading a basic tourist guide,
Oh, totally. Yeah.
you see the grid of the streets, maybe some green blocks for the parks, that blue line for the river, and the guy just kind of points and says, there's downtown.
Right. It's surface level. It's exactly what you need to get from point A to point B
Mm.
without, well, without overthinking it.
Yeah.
I mean, you don't need to know the chemical composition of the asphalt just to drive on the road.
Exactly. It's clean. It's comforting, honestly. We naturally just like things to be visible and easily categorized. We really, really don't want to think about what's underneath.
Right. But then you actually lift the pavement and you step into the world of urban engineering. And suddenly that simple tourist map is completely useless.
Completely.
You're looking at this subterranean landscape that is, honestly, it's overwhelmingly complex. You've got high voltage power grids intersecting with like century-old water mains, massive fiber optic cables snaking around subway tunnels, and sewage systems that operate on these really precise gravity and pressure physics.
It is the absolute definition of invisible complexity. And I mean, the terrifying part is if any single one of those underground pipes bursts, or if a switch fails,
The whole city feels it.
right, the whole beautiful, simple city above just grinds to an absolute halt. The traffic lights go out, the water stops running, chaos.
Yeah, the surface is just an illusion of simplicity, really. It's supported by this massive, highly coordinated, and just heavily engineered backend.
Well, welcome to this deep dive, because today we are taking a jackhammer to the pavement of your digital life.
We really are.
We have this massive stack of architectural blueprints, strategy documents, engineering frameworks sitting right here on the desk, and they reveal exactly how modern enterprise-grade software is built and scaled.
So our mission today is to essentially demystify the back end of the internet for you. Because, you're someone who wants to understand how things actually work under the hood, but without getting bogged down in impenetrable developer jargon.
Exactly. We're taking those highly technical engineering schematics and translating them into plain, actionable language. We are going to explore the physics of the digital world.
And we've got quite the roadmap to get us there.
Yeah, we are strictly following the sequence of materials we've gathered, just to build our understanding from the ground up. First, we have this massive enterprise REST playbook that serves as our foundational philosophy.
The bedrock.
Right. Then we're going to look at a head-to-head framework comparison, essentially choosing the right heavy machinery and concrete for our digital city.
Then deep dive into data formats.
Yep, XML versus JSON. After that, a literal masterclass on the API design lifecycle. And finally, a comprehensive mind map that visually ties every single concept together into one grand synthesis.
Which is great because while a term like enterprise APIs might sound a bit dry or overly corporate on the surface, it's actually the secret, ubiquitous language of the modern world.
It really is.
It's the invisible infrastructure that allows every single app on your phone to function, every financial transaction to clear your bank, every streaming service to deliver ultra-high-definition video to your living room without buffering.
It's everywhere.
Understanding this architecture is exactly like getting those structural blueprints to a digital city. Suddenly you just see how the traffic flows.
Okay, so let's unpack this. I want to start with the foundational philosophy of modern software design. If we look at the evolution of how applications are built, there's this clear dividing line between the old world and the new world.
Oh, very clear.
The new world is defined by something called a microservice architecture. And to understand why microservices are such a big deal, we really have to look at what they replace.
Right. They replaced the monolith, and the monolith was exactly what it sounds like.
I always compare monolithic architecture to like a massive tangled ball of yarn. Or maybe a giant, intricately woven sweater.
A sweater analogy, yeah.
Right. Because if you're a developer and you want to change the color of one thread or fix a fraying piece right in the middle of the chest, you have to pull the whole thing apart.
Exactly.
If one piece of the code breaks, the whole sweater unravels.
That's a perfect way to visualize it. Let's say you built an e-commerce website 10 years ago. In a monolith, your order system, your inventory management system, your user profile system, and your payment processing system.
All the pieces.
Right. They are all compiled together into one gigantic application running on a single massive server.
So they share the same memory, the same database, the same everything.
Exactly. Now, let's say a developer pushes an update to the inventory system, and there's a tiny memory leak.
Oh, boy.
Just a bug that slowly consumes server RAM. That bug in the inventory system doesn't just crash the inventory page. It consumes all the memory on the entire server.
Meaning the order system crashes.
Yep. The user login crashes, the payment system goes down, the entire application completely fails because they're all tied together.
But microservices are entirely different. Instead of a tangled ball of yarn, microservices are like neatly separated Lego blocks.
Precisely. We break that massive application apart into those individual Lego blocks. So the order system is its own standalone application. The inventory system is its own application.
They're independent.
Yeah, they run on entirely different servers or containers. They are independent little engines.
So to use the same scenario, if the inventory block catches on fire because of a memory leak, the order block can still operate.
Exactly. The inventory service might go down, meaning a customer on the website might see a message that says, unable to load current stock levels, but the rest of the website is perfectly fine.
Wow.
They can still log in, they can still view their past orders, and the site doesn't crash. It contains the blast radius of a failure.
That makes total sense from a reliability standpoint. But I also imagine the economic benefits are massive when it comes to scaling.
Oh, the scaling benefits are actually the primary reason the entire tech industry shifted to this model.
Really?
Yeah.
Yeah.
Imagine you are running that e-commerce site on Black Friday. Your order service is going to be absolutely slammed with traffic. Millions of people are hitting the buy button.
Right.
But your user service, which handles things like people changing their profile picture or updating their password, might not see a massive spike at all. I mean, nobody's updating their bio while trying to snag a cheap TV.
Right, right. And in a monolith, if you need more power for the order system, you have to buy a massive new server and copy the entire giant application, right?
Exactly.
Mm-hmm.
You are paying for computing power to duplicate the user profile system, even though it doesn't need it. It's wildly inefficient.
Yeah, that's a huge waste of money.
With microservices, you can scale them independently. You can tell your cloud provider, hey, duplicate the order block 100 times to handle this Black Friday traffic, but leave the user block running on just one tiny server.
So you only pay for the exact computing power you need where you need it.
Exactly.
Okay, so the Lego block approach is vastly superior. But here is where I get hung up. If you break a single application into a dozen different independent blocks, they still have to work together to process a purchase, right?
Right.
The order block needs to ask the inventory block if the TV is in stock. So they need a strict set of rules to communicate across the network.
And that brings us to the core philosophy of our digital city, REST.
REST. It stands for Representational State Transfer, which is frankly a terrible name that explains absolutely nothing to a normal person.
It is a very academic way of saying a highly standardized set of rules for how computers should ask each other for information over the open web.
Okay.
It was actually introduced in a doctoral dissertation by a computer scientist named Roy Fielding back in the year 2000, and it fundamentally shaped the internet.
So let's walk through the rules of REST, often called the constraints, right? Because these really are the constitutional laws of modern software.
Yeah, the rules of the road.
The first rule is client-server separation. The overarching goal here is to make the system simple and evolvable.
Right. This simply means the front end, let's say the app on your phone, which is the client, is completely physically decoupled from the back-end data storage, which is the server.
They don't care how the other one is built.
Exactly.
Meaning, my iPhone app doesn't know if the backend server is running Linux or Windows, or if it's coded in Java or Python.
It doesn't care at all. The client just says, I need data, and the server provides it. The profound benefit of this is independent evolution.
Okay.
A company can completely redesign their mobile app's user interface, hire entirely new front-end designers, push an update to your phone, all without having to touch a single line of code on their database.
Wow. Okay, rule number 2 is where I really want to push back because it has always confused me.
Sure.
The constraint is statelessness. For a conversation between computers to be RESTful, it must be stateless. What does that actually mean in practice?
Think about going to a local coffee shop. If it's a stateful interaction, the barista remembers you. You walk up to the counter and say, hey, I'll have my usual, and they make it.
That's a great experience.
It is. But it requires the barista's brain to store your personal data, your state.
Right. They are holding on to context from our previous interactions.
But what happens if that specific barista goes on break and a new barista steps in? You walk up, say, I'll have my usual, and the new barista just stares at you blankly.
Awkward.
The system breaks down because the state was tied to a specific server. the first barista.
Okay, I see where this is going.
In a stateless architecture, the server is forbidden from storing any session context about the client between requests. It has amnesia by design.
Amnesia by design.
Every single time your phone app asks the server for something, it must include all the information necessary to process that specific request from scratch.
So you walk up to the counter and say, I am user ID 123. Here is my cryptographic authentication token proving who I am, and I want a large, dark roast coffee.
Exactly.
Okay, but I've always struggled with this idea, because if the server forgets who I am every single second, how on earth is my shopping cart staying full as I browse Amazon?
Yeah, it's the million-dollar question.
Like, how does it know I put shoes in my cart 10 minutes ago if it has amnesia? It seems totally counterintuitive to building a fluid relationship with a user.
It does seem that way. If the server is stateless, where does the state live? There are really two answers in modern architecture. Often the state is actually held by the client.
Wait, really?
Yeah, your web browser or your mobile app remembers what is in your cart, and every time you click a new page, it sends the entire contents of the cart back to the server in the background, just saying, here is everything I'm holding.
Oh, wow. So the server isn't remembering my cart. My phone is repeatedly reminding the server what's in my cart.
Precisely. It's doing the heavy lifting of memory. The other method for things that are maybe too complex to store on the phone is that the server takes your request, looks at your user ID, and instantly queries a completely separate lightning-fast database.
Like Redis or something.
Exactly, like Redis. It fetches your cart data, processes your request, and then immediately forgets you again. The core application server itself holds no memory.
That seems like so much redundant communication. Why enforce this amnesia?
Because it is the absolute key to massive cloud scalability.
Okay.
Think about it. If you have 10,000 servers handling traffic for a major website, and your interaction is stateful, the load balancer has to ensure that every single time you click a link, your request goes to the exact same server that remembers you.
And if that specific server crashes?
Your session dies.
Yeah.
You are logged out. Your cart vanishes.
But if it's stateless?
If it's stateless, the load balancer doesn't care. You can send your first click to a server in Virginia, your second click to a server in Ohio, and your third click to a server in Oregon.
Because my request contains all the needed context every single time.
Exactly. Any server on the planet can fulfill it perfectly. If a server dies, the system routes around it instantly and you never even notice.
That is brilliant. So it sacrifices a little bit of network bandwidth because the messages are larger to gain infinite horizontal scalability.
That's the trade-off, yeah.
Okay, that brings us to rule 3, caching.
This one is all about performance and saving money.
So if a million users open their app to look at the front page of a major news site, the server shouldn't have to build that exact same page a million times from scratch, right? I mean, it's asking the database the same question over and over.
Right, that would be a nightmare. So the server can label its response as cacheable. It essentially tells the client, or maybe a routing server sitting in the middle, hey, hold on to this answer for the next 5 minutes.
Don't bother me again.
Exactly. If anyone asks for the front page again, just give them the copy you saved. It absorbs the shock of massive traffic spikes.
Makes sense. Rule 4, uniform interface.
This is the rule that says all the microservices must communicate using the exact same standard conventions. Usually this means using the standard HTTP methods we use every day to browse the web.
But we aren't just browsing, we are interacting with data.
Right, but we use the verbs built into the Internet Protocol. You send a GT request to retrieve data. You send a POST request to create new data.
Like updating a profile or something.
Right, for that you'd send a PUT or a PASSH request to update existing data. And you send a delete request to, well, delete it.
Obviously.
If every single Lego block in your entire company uses those exact same verbs, it's incredibly easy for them to talk to each other. There's no translation required.
Okay, rule 5. Layered system.
This means a client cannot tell whether it is connected directly to the end server or to an intermediary along the way.
So there are middlemen.
Lots of them. You might send a request from your phone. It hits a security firewall. The firewall passes it to a load balancer. The load balancer passes it to a caching server. The caching server finally passes it to the actual application server.
And my phone has absolutely no idea all those middlemen exist.
None. Each layer only knows about the layer immediately adjacent to it. This allows network engineers to insert new security firewalls or performance layers into the chain without ever having to update the code on your phone.
Okay, so those rules define REST. But to really understand why REST is the undisputed king of the modern internet, we have to talk about the protocol wars, because REST wasn't always the default.
Far from it. It was a real battle.
Yeah, for a long time, the formal enterprise-grade approach to computer communication was something called SAP, Simple Object Access Protocol. And from distance, SAP sounds incredibly robust.
It was.
It had strict security protocols, formal contracts, guaranteed delivery. So if SAP was so secure and enterprise-ready, why did REST completely take over the open web?
It's a fascinating piece of tech history, honestly. You are right. For a long time, SA was the gold standard for massive enterprises, especially banks, telecommunications companies, healthcare. It used very rigid, heavy XML formatting.
How heavy are we talking?
Well, the analogy I'd use is that sending a message via SAP is kind of like sending a registered letter through a high-end courier.
Okay.
Have a wax seal. It requires a verified signature upon delivery. It has an incredibly complex legal contract enclosed, and it has layers of protective envelopes.
So it's very safe.
It is highly secure, and it guarantees the message arrives. But it is heavy, it is slow, and it requires a massive amount of overhead just to process the packaging.
And SOP was heavily focused on remote operations, right? Like you were sending a command to another computer to do a specific action.
Yes. SOBP is fundamentally verb-based. You are executing remote procedures.
Yeah.
You would send a massive XML envelope with a command like, say, get invoice details.
But then the world changed. The hardware of the internet changed.
The iPhone launched.
Exactly. We moved from a world of desktop computers plugged directly into corporate Ethernet and high-speed broadband to a world of billions of mobile phones operating on spotty, slow 3G cellular networks.
Yeah, suddenly bandwidth was incredibly expensive. And more importantly, mobile processors were weak and batteries were small.
Oh, right, battery life.
If your phone had to download a massive XML envelope over a 3G network and then use its weak processor to parse through hundreds of lines of complex XMR tags just to extract a single piece of data like your account balance, it drained your battery incredibly fast.
So SOAP was built for a wired world. It was just too bloated for the mobile web.
And that is exactly where REST offered a radically different approach. Instead of focusing on operations verbs, REST focuses on resources nouns.
Meaning, what's the difference in practice?
Well, instead of setting a complex command to get invoice details, in REST, the invoice itself is viewed as a physical resource sitting at a specific URL address on the internet. You just send a lightweight standard HTTP GET request to that URL.
And crucially, REST doesn't care what format the data is in, right? It's multi-format.
Yes.
So instead of heavy XML, developers started returning data in JSON, a vastly lighter text format.
Which made it incredibly fast because REST embraces the stateless constraint. Because it utilizes native HTTP caching and because it can use lightweight JSON, it was perfectly tailored for the explosion of mobile apps.
Which just fit the new environment.
Developers needed speed, flexibility, lightweight payloads to save battery and bandwidth.
Yeah.
REST provided that, and so simply couldn't keep up with the agility required by the modern open web.
That makes perfect sense. The environment dictated the evolution. Okay, so we've established the rules of the road. Let's look at how the digital city is actually zoned and organized. Because if a major enterprise just told 1,000 developers, go build a bunch of microservices using REST, the result would be absolute chaos. You need architectural organization.
Oh yeah, you need to organize your APIs into a structured portfolio.
And a really common way to visualize this architecture is a 3-tier wedding cake.
Right.
At the top layer, you have experience APIs. In the middle layer, you have process APIs. And at the foundational bottom layer, you have system APIs.
It's a masterclass in separating responsibilities.
I was thinking about a high-end restaurant analogy to explain how this workflow actually operates. Tell me if this works.
Let's hear it.
Let's start at the top layer, the experience APIs. These are typically built by front-end app developers. They are adaptations tailored for specific digital touchpoints like a mobile app, a smart TV interface, or a desktop web dashboard. In our restaurant, these are the highly skilled waiters.
Okay, I like this. Keep going.
So the waiters are the face of the operation. They interact directly with the customer. The waiter assigned to the patio might present the menu differently than the waiter in the formal dining room.
Right.
In the digital world, the Experience API for a smart TV might send back big, bold images and simple navigation data, while the Experience API for a desktop financial dashboard might send back dense spreadsheets of data. They tailor the presentation, but they don't actually cook the food.
That's a great analogy. The waiter takes your complex human request and translates it into a standard format the kitchen can understand. They manage the experience of ordering.
Right. Then the waiter takes the ticket back to the kitchen and hands it to the middle layer, the process APIs.
Mhm.
These are usually owned by line of business IT teams. Their job is the composition and orchestration of underlying systems. So these are the kitchen expediters.
Exactly. The expediter is the brains of the kitchen workflow. They look at the ticket the waiter handed them and realize, okay, to fulfill this one order for table 7, I need a steak from the grill station, a salad from the cold prep station, and a bottle of wine from the bar.
But the expediter doesn't cook either.
No, they orchestrate the workflow between different underlying systems, gathering all the pieces, assembling the final tray, and giving it back to the waiter.
Which brings us to the bottom layer, the system APIs. These are owned by central IT. They are the microservices that encapsulate core business capabilities and interact with the actual systems of record. These are the specialized line chefs.
They're the ones actually interacting with the raw ingredients. In our digital city, those raw ingredients are the massive relational databases, the legacy mainframes, and external third-party services like Salesforce or Stripe.
So the line chef at the grill station knows exactly how to cook the steak. The system API knows exactly how to write a query to an ancient Oracle database.
This three-tier separation is brilliant because it protects the core of the business from the chaos of the outside world.
How so? Give me an example.
Let's say your company decides to completely rip out an old database system and replace it with a brand new modern cloud database.
A huge migration.
Massive. But because of this layered architecture, you only have to rewrite that specific system API. You just have to retrain that one specific chef at the bottom layer on how to use the new stove.
Oh.
The process API, the expediter, and the experience API, the waiter, they don't even know the kitchen equipment changed. They just keep passing tickets and getting food. The customer on the mobile app experiences zero downtime during a massive corporate infrastructure overhaul.
That is the power of a layered, decoupled system.
Wow.
And surrounding this three-tier cake, there is an entire ecosystem of platforms to keep it running safely, right?
Yeah.
You have the edge, which consists of firewalls and load balancers acting as the bouncers at the front door, deflecting malicious traffic and routing legitimate requests.
And inside, you have platforms managing the lifecycle. A development platform providing reusable code blocks. A runtime platform, which is the actual engine executing the API logic and handling memory. But perhaps the most critical for the business is the engagement platform.
What does that do?
The engagement platform is basically the community center and the toll booth. It manages consumer interaction, it provides the developer documentation, it generates the secure API keys that let developers access the system, and it handles monetization and rate limiting.
Rate limiting.
Yeah. If a third-party developer builds an app that accidentally goes into an infinite loop and tries to ask your database a million questions a second.
That would crash it.
Exactly. The engagement platform recognizes the spam, steps in, and cuts off their API key before they can crash your servers. An API is only as good as the platform governing it.
So what does all this theory mean when a software engineer actually sits down to write the code? Let's talk about modern data patterns and the concept of the facade. We mentioned earlier that REST relies on noun-based URLs, not verbs. Let's dig into why URL semantics are so rigorously enforced.
It goes back to the uniform interface constraint. Predictability.
The standard rule is do not use verbs. If you want to get customer data, the URL should not be get customers. It should simply be the noun, customers.
Right.
And if you have nested data, don't use verbs there either. Don't use customers 123 get podcasts. Do use customers 123 podcasts. It seems almost pedantic to police how developers name their web addresses, but why is this strict naming convention critical to an enterprise?
Because it establishes an intuitive, unbreakable contract. If every single API in a massive corporation follows these exact same noun-based rules, a developer can guess how an API works before they even open the instruction manual.
It builds muscle memory.
Exactly. If I'm a new developer and I know the URL for a specific customer is customers 123, I instantly know the rules of engagement. I know that sending an HTTP GET request to that URL will retrieve their profile. I know sending a delete request will erase their account. I know sending a PAT-TCH request will update their email address.
Because the verbs are handled by the HTTP protocol itself, not the URL text.
Right. If we allowed developers to put verbs in the URLs, it would devolve into chaos. One team might build delete customer, another team might build remove customer, another team might build archive customer.
You never know what to type.
You'd have to constantly read documentation just to figure out what words people decided to invent that day. Predictability equals development speed.
And speaking of optimizing for development speed, let's talk about the API facade pattern. The overarching goal in modern API design is optimizing APX application programming experience.
APX is a massive focus right now. We talk endlessly about UX, user experience for the consumers tapping on glass screens, but developers are users too.
And if the backend they have to work with is miserable, they will be slow and unhappy.
If an enterprise backend is a horrifying, tangled mess of legacy SOP mainframes, raw SQL databases, and random 15-year-old content management systems, it will take a front-end mobile app developer months to build a simple new feature. They have to learn 10 different legacy protocols just to get the data they need.
So the facade pattern solves this.
It does. The facade pattern essentially puts up a clean, beautiful, ultra-modern storefront in front of a messy, chaotic warehouse.
The mobile app developer only ever talks to the facade. They send a clean, simple, RESTful request. They get back clean, modern JSON data.
Yes.
They have absolutely no idea that behind the scenes, the facade is frantically translating their simple request into a clunky 1990s XML format, routing it to a legacy banking mainframe, waiting for a response, and translating it back.
It entirely shields the app developer from back-end complexity. They get a pristine APX, while the company buys time to slowly modernize the messy warehouse in the background without holding up new product launches.
Okay, here is where we get to some seriously advanced architecture. I want to talk about CQRS, Command Query Responsibility Segregation. This is a pattern used to solve a massive problem with traditional databases under heavy load.
This is one of the most powerful concepts in modern high-scale engineering.
The core problem is that traditional CRU'd applications, meaning applications that use a single database to create, read, update, and delete data, create massive bottlenecks in agile, high-traffic environments. CQRS solves this by literally splitting the pipes.
To understand why we split the pipes, we have to understand the physics of a traditional relational SQL database. Let's use Amazon on Prime Day as our scenario.
Perfect. High stakes, insane traffic.
If you use a single SQL database, it has to handle every single action. When I want to view a product page to look at a TV, that is a read query. When I actually click buy, that is a write command.
Okay.
Now, SQL databases are designed to be incredibly safe and rigid. They guarantee what we call ACID properties: atomicity, consistency, isolation, durability.
So they prioritize absolute data integrity above all else.
Yes. If I try to buy the absolute last TV in stock, the database strictly locks that specific row of data for a few milliseconds to ensure that no one else on the planet can buy that exact same TV at the exact same time. It prevents double selling.
Which is essential. You don't want to charge someone for a TV you don't have.
It is essential. But applying those cryptographic locks takes time and immense processing power. Now imagine millions of people are desperately refreshing the Amazon page just to look at the price of that TV. They are sending millions of read queries.
Right.
If those millions of reads are hitting the exact same database engine that is trying to faithfully process complex write commands and lock rows, the database gets crushed under the weight of the traffic.
It just chokes.
The writes get delayed because the reads are eating all the processor power, and the reads get blocked because the database is locking rows for the writes. The whole system bottlenecks and crashes.
So CQRS solves this by physically separating the traffic at the architectural level.
Exactly. When a request comes in, a router looks at it. If you want to actually buy the TV, your command, the write action, is routed to the highly secure, rigid relational SQL database. It takes its time, validates your credit card, ensures the inventory exists, safely locks the transaction, and protects the business logic.
But when millions of people just want to view the product catalog,
Those queries, the read actions, are routed to a completely separate, NoSQL document store database.
and NoSQL databases like MongoDB or Cassandra are fundamentally different than SQL databases.
Right. They do not worry about complex relational tables or rigid row locking. They are basically massive, flattened filing cabinets designed to just serve up documents incredibly fast to millions of people simultaneously. They are optimized purely for read speed and horizontal scale.
Okay, I see the brilliance of splitting the traffic, but I also see a massive glaring flaw here. If I buy the last TV in the SQL database, how does the NoSQL database know to update its catalog to show out of stock to the millions of people looking at it? They are two separate databases. If they aren't synced instantly, you are showing false data to users.
You've just hit on the hardest problem in distributed systems. And the answer is the event bus, usually a streaming technology like Apache Kafka.
How does that bridge the gap?
When the SQL database successfully writes the order and confirms the TV is sold, it fires off an event message to the Kafka bus. It broadcasts, hey, order completed, inventory for TV is now 0. The NoSQL database is constantly listening to that bus. It hears the event, and it updates its own document.
But there has to be a delay there, right? Like the speed of light, network latency, processing time.
Yes, we call this eventual consistency. It might take 50 milliseconds for the read database to catch up to the write database. During that tiny window, the system is technically out of sync. A user might see the TV as in stock, click buy, and then get rejected by the SQL database.
That sounds really risky for a business. It's a calculated business trade-off. Companies accept the tiny risk of a user getting an item out of stock error during checkout because the alternative, using a single database and having the entire website crash on Prime Day, is infinitely worse. CKRS allows you to handle unprecedented scale by accepting eventual consistency.
That is fascinating. It's an engineering compromise to achieve scale. Okay, let's move to security. Because if we have all these microservices talking to each other and we are exposing them to the open web, we need a robust way to lock the doors.
Security in a stateless REST environment is a very unique challenge.
The gold standard framework for this is OAuth 2.0. This is the security protocol that protects basically everything we do online, but most people have no idea how it actually works behind the scenes. It relies on a concept of delegated access across 4 distinct roles: the client, the resource owner, the resource server, and the authorization server.
Let's ground this in a real-world scenario so it makes sense. Let's say you download a brand new third-party financial budgeting app to your phone.
It promises to analyze your spending habits. To do that, it needs to see your bank transactions. But you obviously do not want to type your actual Chase Bank username and password into this random startups app. That would be insane.
Right. If you give them your password, they have the keys to your entire financial life. They could transfer money, close your account, anything.
So OAuth 2.0 solves this exact problem through delegation. In this scenario, the budgeting app on your phone is the client. You, the human, are the resource owner. Chase Bank's database holding your transaction history is the resource server. And Chase Bank's secure login portal is the authorization server.
So here's how the flow works. The budgeting app, the client, asks me, the resource owner, for permission to view my data. I click yes. But instead of asking for my password, the app redirects my phone's browser to the actual Chase Bank login screen, the authorization server.
Exactly.
I log in securely with Chase. Chase asks me, do you want to allow this budgeting app to view your transactions? I click allow. Chase then issues a cryptographic token and sends that token back to the budgeting app.
Yes. And that token acts exactly like a hotel key card.
How so?
Well, when you go to a hotel, they don't give you the master key to the whole building, right? They give you a plastic card that is programmed with strict limitations. It only opens room 312, it doesn't open the manager's office, and crucially, it expires at exactly 11:00 a.m. on checkout day.
So the token the budgeting app receives has built-in limits.
Exactly. The budgeting app can now take that digital key card to the Chase resource server and say, I'm allowed to read transactions. But the token is explicitly encoded to only grant read access, not transfer funds access.
Oh, that's smart.
And if the budgeting app gets hacked a month later, it doesn't matter because the token already expired. And most importantly, the budgeting app never, ever saw your actual bank password.
That is a remarkably elegant system, but the architecture goes deeper because different types of applications have different vulnerability profiles. The framework uses something called grant types to dictate how securely that key card is handed over.
Right. You wouldn't use the same security protocol for a secure backend server as you would for a public web browser.
Right. If you are building a web server app, meaning a robust backend application where the source code is hidden safely on a private server, you use the authorization code grant. This is considered the most secure method because it involves a backend server-to-server exchange where the client app authenticates itself using a hidden client secret password that the public never sees. It gets a short-lived access token and a long-lived refresh token.
But what if you're building a JavaScript SPA, a single-page application that runs entirely inside the user's web browser, like a complex React app?
Yeah, in a web browser, any user can just right-click, hit inspect, and view source. You cannot hide a secret password inside JavaScript code sent to a browser. Anyone can read it.
Exactly. The environment is inherently insecure. So for those apps, we use the implicit grant. It's a trade-off. It skips the secure backend exchange and just hands the token directly back to the browser via the URL. Because this is riskier? The authorization server will absolutely not issue a long-lived refresh token.
Oh, I see.
If the short-lived access token expires, the user just has to actively re-authenticate. We trade convenience for security.
Now, what do these digital keycards actually look like? In modern REST architectures, we use something called a JWT, a JSON Web Token.
This is a beautiful piece of cryptography that perfectly supports our REST constraint of statelessness.
A JWT is basically a long string of seemingly random characters, but if you decode it, it is divided into three parts: a header, a payload, and a signature. The header just says what type of token it is and what cryptographic algorithm is being used. The payload contains the claims, the actual data about the user.
The payload might be a simple JSON object that says, user ID is 123, name is John Doe, and this token was issued at this specific timestamp. Now, it is crucial to understand that this payload is usually just encoded in a format called base64. It is not encrypted.
Wait, if it's not encrypted, that means anyone who intercepts the token, or the user themselves in their browser, can easily decode it and read the payload.
Yes, they can see the user ID and the name in plain text.
Okay, then how on earth is this secure? If I can decode the token, what stops me from backspacing my own user ID, typing in Jeff Bezos' user ID, re-encoding it, and sending it back to the server to look at his account?
Hackers try to do that every single day. But that brings us to the third part of the token, the signature. And this involves the math of cryptographic hashing.
Walk me through the math conceptually.
When the authorization server creates the token, it takes the header, it takes the payload, and it combines them with a highly guarded secret key, a long password that only the server knows and never shares. It runs all three of those pieces through a one-way mathematical hashing algorithm. The output is a unique fixed-length string of characters. That string is the signature. It is glued to the end of the token.
So if I try to tamper with the payload,
If you alter even a single number in your user ID to try and become Jeff Bezos, you change the input data. When the server receives your altered token, it doesn't just trust the payload. It takes your new payload, combines it with its secret key again, and runs the hashing math itself.
and because the input payload changed, the mathematical output, the new hash, will be completely different.
Exactly. It's called the avalanche effect. A tiny change in input creates a massive change in the output hash. The server looks at the new hash you just generated, compares it to the signature attached to your token, and sees they don't match. It instantly knows the token was tampered with, and it rejects the request.
It is mathematical proof of integrity. And the beautiful part is, this proves why it scales. The server stores zero session state. It doesn't need to look up a database to see if your session is valid. The math itself proves you are legitimate, instantly, using only CPU power.
But, as with all engineering, there is a vital trade-off.
Right, because the server is stateless and amnesic. A valid JWT cannot be easily invalidated or revoked before it naturally expires.
Right, because the server isn't checking a central database every time you click a link. It has no way of knowing if your status changed after the token was issued.
Give me a scenario where that's dangerous.
The fired employee problem. Let's say you issue a JWT to an employee that is valid for 30 days. On day 2, that employee is fired for stealing data. You delete their account in the main database.
Okay.
But remember, the API servers are stateless. They don't check the database. For the next 28 days, if that fired employee sends a request with their token, the cryptographic math will still validate perfectly. The server will let them write in.
Unless you build a manual blacklist.
Right.
A list of revoked tokens.
Yes. But checking a blacklist database on every single request defeats the entire purpose of being stateless and fast. So the industry standard solution is to make access tokens expire incredibly quickly, sometimes in just 15 minutes. You force the client to constantly use a refresh token to ask the central auth server for a new key card, giving the system a chance to realize the user was banned and deny the refresh.
Okay, we have covered an immense amount of foundational theory. We have the architectural blueprints of our digital city. We understand REST, statelessness, CQRS, and JWT security. But now we need to talk about the physical materials used to build the skyscrapers. What framework are the engineers actually using to write the code?
For a very long time in the Java ecosystem, a framework called Spring Boot was the undisputed king. It was the default concrete for building microservices. But a massive paradigm shift in cloud computing has brought a new challenger to the forefront.
And that framework is called Micronaut. We are going to do a head-to-head architectural comparison of Spring Boot versus Micronaut. And the entire battle boils down to one incredibly deep, fundamental difference in how they handle a programming concept called dependency injection.
Let's define dependency injection, or DI, first, so we understand the stakes. In object-oriented programming, you write individual classes to handle specific tasks. A piece of code like our order controller often needs help from another piece of code like an inventory service to actually do its job.
Right. The order controller needs to ask the inventory service if the TV is in stock. It has a dependency.
In the old days, the order controller would have to manually build the inventory service from scratch itself before it could use it. It was inefficient. Dependency injection is a design pattern where the framework itself, the overarching system, injects a pre-built, ready-to-use inventory service into the order controller exactly when it needs it.
Okay, so the framework acts like an incredibly efficient surgical assistant. The order controller, just holds out their hand, and the assistant, the framework, slaps the exact right scalpel, the inventory service, into their palm. The surgeon doesn't need to know where the scalpel came from, they just use it.
That is exactly how it works. Now, both Spring Boot and Micronaut do this perfectly. The critical defining difference between them is when the framework figures out which tools belong in which hands.
Spring Boot uses a mechanism called runtime reflection.
Let's explain Java reflection, because it's a heavy process. Reflection is the ability of a computer program to examine, introspect, and modify its own structure and behavior while it is running.
So when a Spring Boot application starts up, it essentially looks at itself in the mirror. It scans through all of its own compiled code, looking for specific developer annotations, trying to figure out, okay, who needs the inventory service? Ah, the order controller needs it. Let me wire those together.
Yes, it builds the surgical plan while the patient is already on the operating table. The problem is, this introspective process requires a massive amount of computer memory, and it takes time. It might take a Spring Boot application 15 or 30 seconds to fully boot up and wire itself together before it can accept a single user request.
Now contrast that with Micronaut. Micronaut uses compile time dependency injection.
Let's use an analogy here to explain the difference.
I've got one. Let's say compile time DI is like packing your suitcase perfectly before you leave your house for the airport. You analyze your itinerary, you lay everything out on the bed, you know exactly what outfits go together, you fold it all neatly, and you zip it up. When you arrive at your hotel, your suitcase is lightweight, and you can instantly start unpacking because everything is already perfectly organized and wired together.
I love that. At compile time, meaning when the developer actually builds the code on their laptop before deploying it, Micronaut analyzes the entire application. It figures out every single dependency, every single connection between classes, and pre-writes the wiring logic.
It does all the heavy analytical lifting before the app even starts.
Yes. So when the app actually launches on the server, it doesn't need to look in the mirror. It just executes the pre-written instructions.
So Spring Boot's runtime reflection would be like showing up to the airport with an empty suitcase and trying to figure out what you need to pack while sprinting through the terminal. You're throwing random items from the duty-free shop into your bag, trying to read the weather report on your phone while running to the gate. It requires massive cognitive load and slows you down.
Exactly. Now, you might ask, why does a 30-second startup time matter? In the old days of monolithic applications where you started a server on January 1st and just left it running continuously until December, a 30-second startup delay didn't matter at all.
But the cloud changed the economics of computing, specifically the rise of serverless architecture, like AWS Lambda.
This is where Micronaut's architectural advantage becomes overwhelming. In serverless architecture, your application does not run continuously. It sits completely dormant, costing you $0. When a user clicks a button on your website, Amazon instantly spins up your code, executes the function, and shuts it down again. This might happen 10,000 times a minute.
And crucially, Amazon charges you by the millisecond for compute time and by the megabyte for memory usage.
Precisely. If your Spring Boot application takes 15 seconds to boot up every single time a function is triggered, what we call a cold start, because it's doing heavy runtime reflection, two things happen. First, the user experiences massive, unacceptable lag on the website. Second, your cloud computing bill goes through the roof because you are paying for 15 seconds of heavy CPU usage just to start the app.
But Micronaut's compile time DI means the application can cold start in milliseconds with a tiny memory footprint. It is tailor-made for the economics and performance demands of modern, containerized, serverless cloud environments.
Micronaut was built from day one, assuming it would live in a distributed microservice cloud. It natively integrates features like service discovery via console and client-side load balancing directly into the runtime, whereas Spring Boot often requires developers to bolt on external third-party libraries to achieve the same cloud-native features.
I want to push back a little here, to be fair. If Micronaut is so vastly superior for the cloud, why does anyone still use Spring Boot?
Because Spring Boot has a massive decade-long head start. It has an enormous ecosystem, incredibly robust community support, and thousands of plugins for edge case integrations. If you need to integrate with a legacy enterprise system, there is a 99% chance someone has already written a Spring Boot plugin for it. It also has a slight edge in external caching providers, natively supporting robust systems like eCache and Caffeine. It's an incredibly powerful, mature framework.
It's the safe, established choice. But for new, high-performance, cost-sensitive cloud deployments, Micronaut is the specialized sports car. And despite the advanced compile time magic happening under the hood, the actual developer experience is surprisingly straightforward.
That's the beauty of modern Java toolchains. You don't need a PhD to use it.
You set up your environment using modern tools SDKM to manage your versions, a modern Java development kit like JDK21, and build tools like Maven or Gradle. And the code itself is remarkably clean. You just create a plain Java class and add a single annotation like @controller.
Hello.
That one simple annotation tells the Micronaut framework during the compile phase to automatically wire that class to the hello web address. It abstracts away all the complex network routing logic.
So we have our heavy machinery.
Right.
Now, we need to decide what language these microservices will actually speak to each other across the network. The framework is the engine, the data format is the fuel. And we have a heavyweight title fight here. XML versus JSON.
For a long time, XML extensible markup language was the undisputed king of web data interchange. XML is defined by its structural anatomy, a strict hierarchical tree wrapped in opening and closing tags. Anyone who has looked at early web code recognizes it. If you want to send data about a book, it looks like this. Book category, fiction, then a nested tag title, the stranger title, then author Albert Camus author, and finally closing it out with book.
It is entirely self-descriptive. A human can look at that block of text and know exactly what data it contains. And if you pair it with a complex external schema, you can strictly validate that the data is formatted perfectly before accepting it.
But the weaknesses of XML are precisely why it lost the war for modern APIs. Let's talk about verbosity and parsing.
Think about the payload size. If you are a database sending a list of 10,000 books to a mobile phone app and every single book title is surrounded by a title and title tag, a massive percentage of the bandwidth you are using is just transmitting those structural tags, not the actual valuable data itself.
And as we discussed with SOAP, in a mobile environment with limited bandwidth, that bloat is unacceptable. But it's not just the file size, it's the parsing speed, right?
Exactly. When the phone receives that XML file, it has to use a dedicated XML parser to read through the entire document, build a complex hierarchical tree in its memory, and then navigate that tree just to find the author's name. It's computationally expensive.
Which brings us to the lightweight speedster, JSON JavaScript object notation. It abandons the heavy tagging system entirely. Its structural anatomy is all about simple key-value pairs.
It uses curly braces for objects and square brackets for arrays. So that exact same book data is simply title, the stranger, comma, author, Albert Camus.
No closing tags, just the key and the value.
It's incredibly clean. But the real advantage is how machines read it. JSON maps perfectly to the object-oriented data structures used in almost every modern programming language. A Java program or a Python program doesn't need a heavy parser to build a tree. It can translate JSON text directly into native code objects almost instantly.
And JSON handles native data types much better than XML. In XML, everything is treated as a text string, unless you build a complex schema. If you send the year 1942, it's text. But JSON natively supports strings, numbers, and booleans, so published. 1942 is automatically recognized as an integer. In stock, true is automatically recognized as a boolean. The developer doesn't have to write extra code to convert the text 1942 into a math-ready number. It saves processing cycles.
But there is a fascinating quirk about JSON that highlights exactly what it is designed for.
I know exactly what you're talking about, the lack of comments. In XML, a developer can leave a comment in the code using a specific syntax to leave a note for another developer. Something like, note, this data is deprecated down.
But JSON explicitly does not support comments. The creator of JSON, Douglas Crockford, actively removed the ability to leave comments because developers were using them in weird ways to inject parsing directives.
It enforces the idea that JSON is strictly a machine-to-machine language. It's built purely for raw data transfer speed. It is not built for humans to leave little notes for each other inside the payload. If you put a comment in a JSON file, the parser will choke on it and fail.
And implementing this in modern frameworks like Micronaut is incredibly elegant. You don't write any code to generate those curly braces.
Right. You define a domain object, a plain old Java object or POJO. You write a Java class with a title and author field. Then you just add an annotation to your controller, like at produces media type.txt.json.
The framework does all the serialization magically behind the scenes. It takes your Java object, formats it perfectly into JSON, and shoots it across the network. And to test all this, developers use a tool called Postman.
Postman is essential. It acts as a specialized raw web browser for developers. It lets you construct precise HTTP requests, send them to your API, and examine the exact JSON payload and security headers that come back. It's how you prove your API is speaking the language correctly before you release it.
Okay, so we have the architectural blueprints, we have the fast Micronaut framework, and we have the lightweight JSON data language. We know how to build a single microservice perfectly.
But building one service in a vacuum is easy. How does a massive enterprise with thousands of developers across the globe actually manage the creation of hundreds of these APIs without descending into total chaos?
That moves us from the tactical engineering level to the strategic organizational level. You have to master the API design lifecycle.
The overarching strategy for modern enterprises is a relentless focus on APX API user experience. The philosophy is that an API is a product. And just like any consumer product, if it has a terrible user experience, it will fail.
In a massive corporation, internal adoption is critical. Let's say central IT spends $1 million building a new system API to access customer data. If that API is confusing, poorly documented, and hard to use, the mobile app teams will simply refuse to use it.
What do they do instead?
They will go rogue. They will build their own redundant shadow IT connections directly to the database to get the data they need faster. Suddenly, you have dozens of undocumented pipelines tapping into your core systems. It's a security nightmare, and it leads to massive code sprawl. Good APX is the only way to ensure internal compliance. You have to make the official way the easiest way.
So how do you guarantee a good experience? The strategy dictates two paths. If you have complex legacy systems, you use the facade strategy we discussed earlier to hide the mess. But if you are building something new, you use the greenfield strategy. And the defining characteristic of this strategy is API-first design.
This is a major paradigm shift. In the old days, developers would build a database, write all the back-end logic, and then at the very end, bolt an API on top of it so the front end could access it.
But API-first means you flip that process completely upside down. You use simulation-based design, meaning you do not write a single line of back-end database code until you have completely designed the API contract, set up fake mock servers, and let the front-end mobile developers actually play with it.
It's like building a cardboard mock-up of a house layout and having the client walk through it before you pour the concrete foundation. If the mobile team uses the mock API and says, actually, the way this JSON data is structured is really awkward for our screen layout, can you combine the first and last name fields? It costs you absolutely nothing to change the design document.
But if you had already spent 3 months coding the Java backend and structuring the SQL database, that minor change request would be an absolute nightmare. API-first design prevents massive wastes of engineering time.
And that leads into the formal corporate pipeline. You start with domain analysis to prove the business value. You design the architecture, you prototype with mock servers, you implement the actual code, and finally you publish the API.
And when you publish it, it becomes a binding contract, which brings us to the modeling wars. How do developers write these contracts?
An API model is a schema. It is a definitive map that says, if you send an HTTP request formatted exactly like this, we guarantee we will send a JSON response formatted exactly like this.
The heavyweight champion of modeling tools is OpenAPI, formerly known as Swagger. The format is JSON. Its philosophy is implementation first, and its key strength is a massive community and the ability to automatically generate server code directly from the model. It is ubiquitous.
But there is a challenger focused entirely on the design-first philosophy, RAML, RESTful API modeling language.
The interesting thing about RAML is its format. It uses YAML instead of JSON. Why is YAML preferred for the design-first phase?
Because YAML is vastly easier for a human to read and write than JSON. JSON requires strict curly braces, commas, and quotation marks everywhere. If you miss one comma, the file breaks. YAML will remove all the syntax noise. It relies purely on clean indentation and line breaks to show data structure.
So if you were an architect sitting in a conference room with a non-technical business analyst trying to sketch out how an API should behave, YAML is much friendlier to draft in. It reads like an outline.
Exactly. RAML enforces that human-centric top-down design process.
Now, to ensure these contracts are actually functional, enterprise strategy dictates strict RESTful best practices. These are the rules every developer must follow to prevent chaos. We already beat the nouns, not verbs rule to death, but let's talk about mandatory versioning.
This is critical for enterprise stability.
The rule is to always use a version prefix in the URL, like view on podcasts. Why is that so important?
Because once you publish an API contract, it is sealed. Let's say you build V1 users, and it returns a JSON object with a single field called full name. Thousands of mobile apps are built relying on that exact structure. 6 months later, you realize you need to separate it into first name and last name. You cannot simply change the code on the server.
If you change the JSON structure, the mobile apps looking for full name will crash instantly. You broke the contract.
Precisely. And in a global enterprise, you might bring down partner systems across the world. So instead, you deploy the new code at a new URL. V3 users. You leave V1 users running exactly as it was, untouched. You then notify all the developers, hey, V1 is now deprecated. You have 12 months to update your apps to point to V2. This guarantees zero downtime for the end users while allowing the system to evolve.
Another strict rule: simplify error handling. The standard is to use 3 baseline HTTP status codes, 200 for OK, 400 for bad request, and 500 for internal server error.
The HTTP protocol has dozens of hyper-specific error codes, but for a clean API, keep it simple. If the client asked for data and got it, return a 200. If the client sent a malformed request or asked for something they aren't allowed to see, return a 400. That tells the client, you messed up, fix your request.
And if the server's database just caught on fire?
Return a 500. That tells the client, we messed up, try again later. It makes it incredibly easy for the front-end application to know how to react to failures.
The final best practice is consistent pagination. If an API is asked for a list of 100,000 users, it obviously shouldn't send a 50-megabyte JSON file all at once. It sends them in chunks.
There are 2 main strategies for this. The offset limit strategy, which is like saying, skip the first 50 results and give me the next 25. Or the start count strategy, which is essentially the same math.
The strategy chosen doesn't really matter. The critical part is the word consistent. An enterprise must choose one style and enforce it globally across every single API in the portfolio. You cannot have the inventory API use offset limit and the user API use start count. That ruins the APX because developers have to constantly check the documentation to remember which math to use.
All of these strategies, versioning, error codes, pagination facades, exist to serve the human ecosystem. The API providers deep in the central IT department designing for reusability, the API consumers building the client apps, and ultimately the end users interacting with the final product. Every single deep technical architectural decision ultimately impacts the speed and reliability experienced by the end user on their smartphone.
We have covered an immense amount of ground today. We've gone from the conceptual philosophy of REST down into the heavy back-end machinery with Micronaut, explored the cryptographic math of stateless security tokens, and mapped the strategic organizational lifecycle. It is a massive, complex system of moving parts.
It is the absolute definition of a complex, interconnected system.
Which is why I am incredibly grateful for the final conceptual tool we have to tie this all together. It is a visual mind map, synthesized from all these concepts. If you, the listener, have felt overwhelmed at any point by how all these different acronyms and rules connect, this mental model is how you bring order to the chaos.
A mind map is the perfect tool for systems thinking. Because in architecture, you can't just memorize discrete facts. You have to understand the relationships and the domino effects between decisions.
Let's trace the logic through this map. At the center, we have our engine, Micronaut for RESTful APIs. If we trace a conceptual line outward, every decision radiates from the foundational principles of REST. The constraint of statelessness isn't just an abstract rule, it dictates our security model.
Exactly. Because the REST constraint demands that our servers have amnesia and maintain zero-session state, we are forced to abandon traditional server-side session cookies. We must use cryptographic JSON Web Tokens, JWTs, on the client side to prove identity mathematically.
And because we are using stateless JWTs, the load balancers at the edge can instantly and indiscriminately route traffic to hundreds of duplicated microservices without breaking user sessions.
Which leads to the next connection. Because we now have hundreds of microservices handling massive, globally distributed traffic, traditional SQL databases become the bottleneck. They lock up. Therefore, we are forced to implement the CQRS pattern. We must split our reads into a highly scalable NoSQL document store, and we must use an event bus like Kafka to keep them eventually consistent.
And to run those hundreds of microservices cost-effectively in a serverless cloud environment, We cannot use heavy frameworks that rely on runtime reflection. We need lightweight, instant cold starts. Therefore, we choose Micronaut and compile time dependency injection.
And finally, to ensure that these hundreds of independent microservices can actually talk to each other and be understood by the mobile apps consuming them, we enforce strict API design contracts using OpenAPI, versioning, and standardized JSON data formats.
It is a perfect domino effect of architectural logic. Every single engineering choice necessitates the next. You can't just pick a database or a security protocol in a vacuum.
Systems thinking. It's understanding how a decision about a lightweight data format, like JSON, impacts a security protocol like JWT, which impacts server memory usage due to statelessness, which ultimately impacts the financial cost of running a serverless cloud infrastructure with Micronaut.
It is understanding the entire subterranean blueprint of the digital city. Well, we have reached the end of our deep dive, and I want to congratulate you, the listener, for making it through an incredibly dense, advanced topic. We have unpacked a tremendous amount of engineering knowledge today. You now understand the core philosophy that governs the web, the constraints of REST. You understand the specific engine-powering modern cloud infrastructure compile time dependency injection.
You understand the physics of data formatting with JSON versus XML. You understand the rigorous lifecycle and modeling strategies used to create unbreakable API contracts. And you deeply understand the facade patterns and CQRS pipelines used to protect legacy systems and achieve massive planetary scale.
You have a complete high-level view of how enterprise software is actually constructed in the real world. And I want to connect this directly back to your everyday life. The next time you are standing in line at the airport and you open your airline's mobile app and instantly see your updated flight gate and departure time, I want you to think about what just happened in that half second.
You'll know that your phone didn't just casually ask a server a simple question. You'll know that your app sent a stateless, RESTful HTTP request. You'll know it hit a load balancer at the edge of the network. You'll know an authorization server cryptographically verified the mathematical signature on your JSON web token. You'll know an experience API acted as a facade, routing your clean request to a highly optimized Micronaut-powered process API, which orchestrated a lightning-fast query to a NoSQL document store that had been eventually synced via a Kafka event bus from a secure relational database main system.
And you'll know that all of that complex plumbing executed flawlessly in milliseconds because thousands of engineers followed strict URL semantics and design contracts to build a system of independent microservices that scale perfectly to handle the rush. The invisible complexity of the subterranean city will suddenly be visible to you. But before we sign off, I want to leave you with a final forward-looking question to think about based on the strategic life cycle we reviewed. We talked heavily today about APIs being a contract between humans. We talked about providers designing for reusability, consumers building the clients, and optimizing the API user experience APX for human developers.
Right. We rely on humans to read the OpenAPI documentation in YAM or JSON and mentally agree on the structure before they write the code.
But as AI systems and large language models become increasingly advanced and autonomous, what happens when AI agents start reading these OpenAPI schemas themselves? What happens when autonomous systems start negotiating their own data contracts, dynamically discovering new services on the network, and building custom system APIs on the fly without a human developer ever writing a single line of integration code? How does the entire concept of API user experience fundamentally change when the primary user parsing the documentation is a machine?
It's a fascinating and slightly terrifying thought. The strict noun-based URLs, the predictable error codes, and the highly structured JSON formats we built to make things easier for human programmers, well, they are actually the exact perfect training data for an AI. We have inadvertently built the perfect standardized interface for AI agents to learn how to manipulate the physical and digital world autonomously.
It's a brave new architectural world out there, and the blueprints are constantly evolving. We want to warmly thank you for joining us on this deep dive. Keep questioning the surface-level simplicity and keep exploring the invisible blueprints of your digital city. Until next time.